Welcome to the Chapter 11 review on intermolecular or forces that include intermolecular forces. Pause the video now and make sure that you have a piece of paper, pen or pencil out. Helps to have a periodic table out as well. And make sure that you're ready to write down a bunch of notes here. Chapter 11, forces. Forces in molecules or compounds decide what phase of matter the substance is going to be in, and or whether or not a substance will mix or be miscible with another substance. For instance, oil and water don't mix because they have different forces that attract each other. Water changes from solid, liquid to gas at various temperatures depending on its intermolecular forces versus something like carbon dioxide, which changes from solid to liquid to gas as well, but it depends on its forces that hold it together. We're going to make a small table here to relate the different types of forces that we learn here in chemistry. So get ready to draw all the way across your paper so you can organize it. First of all, things that are made of molecules. Things that are made of molecules are things that are only covalently bonded. They are made up exclusively of non-metals. Exclusively of non-metals. And we spend the most time talking about these because they have a lot of different types of intermolecular forces that hold them together. These are things like water, ammonia, NH3, all of our acids like HCl or HF or things like that. All the things that are made of non-metals. Most carbon-containing compounds like methane, sugar, sucrose, those types of things. All non-metal molecular compounds. You need to be able to differentiate between these and ionic-containing compounds. Ion-containing compounds contain a metal. And remember, metals on the periodic table are the most abundant thing. Everything over here is metals, except for hydrogen. Okay? But a lot of the things we study are over here that contain only nonmetals. But keep it straight. If it's got a metal in it, or if it's got two polyatomic ions stuck together, they're held together by what's called an ionic bond, which is an electrostatic attraction between a positive metal or a positive cation and a negative anion. These are super strong intramolecular forces. Next are pure metals, like iron, nickel, cobalt, chromium, gold. They're held together by metallic bonds. These have what are called delocalized electrons that stick them together. Doesn't necessarily mean it's got a high, lower, middle, melting, boiling point. It just means that the electrons are free to flow around a lot. Last one are a couple of special ones. These are ones where atoms are just stuck together, like for example in noble gases, or when carbon or sulfur, diamond is a form of carbon, are just stuck together. These are known as covalent network substances. They're super strong, and they have really high melting points. Super strong, and they have really high melting points. Anytime you see diamond, carbon, pure sulfur, pure carbon, like graphite, always think some type of covalent network bonds that are strong and stuck together, and they're made up of only one single thing. All right, those are the four classes. The four classes tell you what the intramolecular forces are, or the intra-forces are that hold these things together. In molecular substances, it's covalent bonds that hold them together. And to break a covalent bond means that you're changing the substance. You're not just changing from a solid to liquid to a gas. You're actually breaking the bond. In ionic substances, they're held together by ionic bonds. And when you make an ionic substance go from a solid to liquid, you're simply taking it and making it into its ions that are free, I'm going to use the word wrong, but floating around in the liquid. And then when you boil them, they're making them into gases, and then lots of reactions happen with those. Ionic compounds have really high melting points compared to molecular things almost all the time. Metallic things are held together by metallic bonds. That's their intrametallic force. A lot of delocalized electrons that make that happen. And then we already talked about these atomic structures and noble and covalent network things. Now, keep this straight in your head, because you must differentiate between these classifications to be able to understand the difference between intramolecular forces and intermolecular forces. We spend almost all our time during this chapter talking about the intermolecular forces experienced by covalently bonded things. Remember, covalent bonds are the things that hold carbons to hydrogens, or nitrogens to oxygens, or chlorines to hydrogen. Those are the covalently bonded intramolecular forces. The intermolecular forces are like the interstates. They connect states. They're the roads that go between and across many, many states. They're the big forces. They're the things that are broken when we change from solid to liquid to gas, or gas to liquid solid in these molecular substances. Keep that straight in your head. The three types of intermolecular forces that we spend a lot of time on, and we will spend 5 minutes on here, are London dispersion forces, dipole-dipole forces, and hydrogen bonds, which are really nothing more than a special case of dipole-dipole forces, and we'll go to a lot of details on the next page. Finally, the intermolecular forces for ionic, metallic, and noble gas, or covalent network compounds, are actually the forces that hold them together originally. The intra and intermolecular forces are actually the same over here for these. To change from solid liquid to gas here, you're simply moving those ions further apart. And that's why it takes lots of energy to melt something like sodium chloride, or I put down copper sulfate right here. To separate those ions from solid to liquid, make liquid copper sulfate, you take these ions and separate them further apart and make them free floating from one another. Metallically bonded things, we don't know for sure whether or not they're going to be high or low melting. Obviously, a liquid or a substance like mercury is a metal and has metallic bonds, and it's a liquid at room temperature. But then a substance like tungsten, another metal, has metallic bonds, and it doesn't melt until like 1700 degrees Celsius or so. So these delocalized electrons don't necessarily tell us whether it's high or low melting. They just tell us that they have other properties like conductivity. They're good conductors of electricity. They're malleable, they're ductile, they can be hammered into shapes or formed into different things. Lastly, covalent network, to melt those, or I guess boil, change them into a gas, you need to break some of these covalent network bonds, and these are super strong. Like diamond has a super high melting point, okay, because these covalent network bonds hold them together. Differentiating between these classifications is key in all of the questions that you'll see a little bit later on. Next page of notes, though, get another page out. We're going to look at details of these intermolecular forces right here. We're focusing in on this area now, and we're kind of ignoring these, even though these also come into play in questions on the AP exam. All right, London dispersion forces. London dispersion forces occur in all atoms and nonmetal compounds. These happen because there's an instantaneous polarization of electrons throughout a molecule. So for example, if you have two carbon dioxide molecules, at one instant or snapshot in time, you might have a buildup of more electrons over here on this side of the molecule, because a couple extra electrons from this oxygen came closer to the carbon, and some of carbon's electrons came over here closer to oxygen. At the same instant in time, perhaps the electrons did the same thing over here in this carbon dioxide molecule. And the electrons built up over here, which means a lack of electrons here. A lack of electrons gives it more of a positive charge. This positive charge then connects to this buildup of negative charged electrons over here. This positive-negative attraction right here is known as an instantaneous polarization of electrons and is given the term a dispersion force, or a London dispersion force, if that's what you want to call it, where molecules connect to other molecules due to this instantaneous polarization of the electrons. The next instant, doesn't happen. The electrons go back to where they normally are, and then it maybe connects to another one. Bottom line is that the bigger the molecule, the more electrons it has, and therefore more London dispersion forces. How do you know if the molecule is bigger? Well, two ways. One, if it has a larger molar mass, obviously it has more electrons. Larger molar mass means more protons, therefore more electrons. And then second of all, if it has more surface area. Okay? If a molecule's shape gives it more surface area, then it can have more London dispersion forces. So if you have two substances with equal molar mass and you want to know which one's going to stick together better, it's the one that's more spread out or gives more surface area that's going to stick together better and therefore have a higher melting or a higher boiling point. Second one, dipole-dipole forces. These occur between polar molecules. Now, determining whether a molecule is polar is important too. A polar molecule is one that is asymmetrical. A polar molecule is one that is asymmetrical, meaning if you slice it exactly in half, they have different halves. And you can see if I slice HCl in half, obviously I have different halves. If I slice ClCl in half, obviously I have the same halves. And so this one would be nonpolar, this one would be a polar molecule. And asymmetry allows us to know if a molecule is polar or not. This guy right here, even though I drew it kind of weird, is totally symmetrical. 109-degree bond angles right here between the carbon-hydrogen, hydrogen-carbon-hydrogen bonds. Whereas this guy right here with a fluorine in it, obviously it's asymmetrical because if I cut it in half up this direction, realizing that these are 109.5-degree bond angles, I'll end up with a different half over here than over here. Water is a great example of something that's a polar molecule. It is totally asymmetrical. You might look at it and say, oh, no, it's symmetrical, but what happens if I cut it in half this way? Well, then I end up with two unshared pairs of electrons here and hydrogens over here. Unshared pairs of electrons are almost always a good indication that a molecule could be very, very much so, is very likely going to be polar because you can cut it and it's going to be, first of all, weirdly shaped a little bit because these unshared pairs of electrons take up more space and their bond angle is a little bit uneven as well. Last type of intermolecular force for covalently bonded molecules are hydrogen bonds. This is a special dipole-dipole force. Hydrogen bonds are a special dipole-dipole force. They are when H, a hydrogen, is connected to an F, an O, or an N, a fluorine, an oxygen, or a nitrogen, a phone in a molecule. It can be connected to one or more in a molecule, but as long as it happens in one place, that one place has the opportunity to experience hydrogen bonding. The reason it happens is because the hydrogen molecule electron, the hydrogen molecule's electron is pulled very closely to the nitrogen, the oxygen, or the fluorine due to these three elements' electronegativity, therefore exposing the positive nucleus area to attract to other things. Here's a couple of good examples. Here's ammonia. Ammonia, of course, has a hydrogen bond possibility because nitrogen is bonded to hydrogen. The electrons are pulled really close to the nitrogen, giving it more of a positive charge here. Here's another example with water where it has more of a negative charge here because the electrons are pulled close to the oxygen. And that's why ammonia and water attract each other so well. They both have similar characteristics. Here's another one where a hydrogen is attached to a fluorine. The hydrogen atom's electron would be pulled close to the fluorine, giving more of a partial positive charge here, more of a partial negative charge here. And remember, we use this small letter delta, meaning partial positive, and we draw it an arrow indicating there's a partial negative charge over here, and the electrons are pulled this direction. Okay? So, why all the big fuss about these intermolecular forces? Why are they important? Well, the stronger the intermolecular forces, the higher melting point and the higher boiling point. If they have the same type of intermolecular forces as something else, they're more miscible, or they're more mixed together, easier to make a solution. Now, before we go on and look at a couple of problems, let's make sure that you're not lost by saying I'm only focused on LDF, dipole-dipole, and hydrogen bond. Those are important, but you also must be able to differentiate between these molecular forces, the ionic forces, the metallic forces, and the atomic forces, and know that these things are held together by intramolecular forces called covalent, ionic, metallic, or covalent network bonds. but the molecules themselves are held together by intermolecular forces. And only these guys over here experience the ones that we were talking about called LDFs, dipole-dipole, and hydrogen bonds. Let's look at some example problems from past AP exams that use these. First of all, here's 2006 question number 6. Write this down on your paper. Write this down on your paper. 2006, number 6, letter A. The structures for glucose and cyclohexane are shown below. Here we go. Here's glucose and cyclohexane. Identify the types of intermolecular attractive forces. Well, if you look at this glucose molecule right here, you'll see that it has all nonmetals, first of all. And then you'll look over here at cyclohexane, and you notice that it also has all nonmetals. So that means it must be one of these things that experiences molecular forces. It is covalently bonded. As a matter of fact, you don't draw Lewis dot structures for anything except for covalently bonded things. It doesn't have a metal in it. It's not metallic bonds. It's not like just pure carbon or something like that. So it's none of these guys. Now we're stuck in this world over here where we're going to look at London dispersion forces, dipole-dipole forces, and hydrogen bonds. Well, what kind of forces do all molecules experience? Well, you better say London dispersion forces because they all do. So that's one of the type of intermolecular forces in both of these, okay? Then secondly, remember there's this thing called dipole-dipole and this special case called hydrogen bonding. Well, look what they have. Are they polar? Well, this one is definitely polar. It looks wacko. It's got an OH is stuck over here, CH2OH stuck off over here, OH is stuck off all corners. It is definitely not symmetrical. So it's going to have some type of dipole-dipole force. But wait, remember, if hydrogen is connected to a phone, an FO or an N, it could experience this special case of dipole-dipole force called hydrogen bonding. And so this guy right here should not only experience London dispersion forces, but should also experience hydrogen bonding. This guy right here, perfectly symmetrical, if you look at it, perfectly symmetrical means it's nonpolar, and therefore the only thing it's going to experience is London dispersion forces. Let's see if we were right. Hydrogen bonding or dipole-dipole interactions or van der Waals interactions, London dispersion forces may also be mentioned. 1 point earned for the correct answer for glucose right here. So they could say LDFs, and then they could also say hydrogen bonding or a special case of dipole-dipole. In cyclohexane, only London dispersion forces or dispersion forces are okay as well. So you can see those are this has at least 2 types of forces. This one, depending on how you name them, this one has only 1 type of force right here. Next, glucose is soluble in water, but cyclohexane is not soluble in water. Explain. Remember we talked about here, why is it important to know these forces? First of all, the stronger the forces, the higher the melting and boiling point. But now they're asking about dissolving. Well, if they have the same type of intermolecular force, then they're miscible, or they can make a solution. So it says it's soluble in water. What kind of forces does water experience? Well, remember, water is a polar molecule, and therefore it experiences dipole-dipole forces. And as a matter of fact, it's a special case called hydrogen bonding because it's got an H connected to an FO or an N. So it's got a positive and a negative charged area here. Well, that means that something with hydrogen bonding would dissolve in it. And as a matter of fact, glucose right here does dissolve in water, whereas cyclohexane has none of these forces, so it's not going to dissolve. So you could say the hydroxyl groups in the glucose molecule can form strong hydrogen bonds with the solvent, known as water. So glucose is soluble in water. In contrast, cyclohexane is not capable of forming intermolecular attractions with water because there's no hydrogen bonding. So the water-cyclohexane interactions are not as energetically favorable as the interactions that already exist among the polar water molecules. Okay, a couple of other ways that they describe that as well. If you look on the back here, part 2 of this goes into a process about phase change, and then they ask a question about water too. So it says, consider the 2 processes